I'm priding myself on not procrastinating this year.
Okay, good morning everybody. Before I get started, just one announcement for the SI sessions. We have an SI session this Monday, 17th of September, between 8:45 to 10 p.m. in ISB 329. There may be change of the room or the location. I'm going to send you an email about it. The other SI session is going to be Thursday, the 20th, from 5:30 to 6:45, also ISB 329. It may be subjected to changes of location. I'm going to send you an email about that. And I'm going to send kind of the schedule for all the SI sessions that's going to take place from now on. And I may post it on Moodle so that you'll be able to see that. Okay, so by the way, all these dates I'm going to post the before and after, so all these dates going to be in Moodle in the first slide. So Friday we were talking about the periodic table, the main elements and the transition elements. So today we're going to show you some of those metals. Then we can So Jay's going to show you some of the metals. The titanium. This is the titanium. Good. This is tin. Iron. Do we have copper or something? Okay. Copper. Okay, we have lead also. Okay, so those are kind of the metals between transition and the main one. We talked about nitrogen, that it always exists as N2, and it is a gas, but sometimes we just make it into a liquid. We call it liquid nitrogen. Definitely under certain pressure and temperature condition, it's kept to the liquid form, and it is very useful, especially in biology. So we're gonna do everyone can see that. So, the liquid nitrogen, first of all, okay? It's liquid, don't be scared. It's nitrogen, it's what's in the air. Yeah. And then directly it goes into the gas, and it is usually used to freeze cells in the tissue and then kind of make them into micro slices. So just to explain that to you, we have flour in here. It's flour, nothing. So Jake can now put it inside this for about 10 minutes or so, a little bit. And then he's gonna do one by one flour by one. He's gonna hit it on here, and you're gonna hear that it have now a glass property. It's gonna break down as glass. Okay, let's start with one of them. Okay, just hit it. Yeah. So we'll clean after the class, but this is how. So usually liquid nitrogen is very useful whenever you want to freeze something and then cut it, because it's kind of things get brittle and you can cut it. It's used for tissues, for cell tissues and stuff like that. And now let's go back to both presentations. Okay. So this is, so we talked about sodium and how they interact with water violently as we go down. The periodic table is kept more violent. We talked about liquid nitrogen. Definitely there are much more interesting stuff in the periodic table, like mercury, the only metal that is liquid that has been used for a long time inside the thermometers, not anymore because it's dangerous, it's environmentally not friendly, so they aren't using it anymore, but it's the only metal that is in a liquid form at room temperature. Today we're gonna keep going and we're gonna talk about molecules and compounds. So if you remember in the very first lecture of this class, we talked about pure material being either element or compound. So today we're gonna talk about these compounds. If I have a compound mainly as we defined it, it is a combination of two or more atoms. Now if I have, for example, H alone is an atom. F alone is an atom. When they combine together, we call this a molecule. And here I mean by combination, there is a bond in there. It's not just, oh, I'm combining them together. This is a molecule. As we talked about before, that the compound or the molecules and its atom, they don't have the same properties. An example of that, if you remember copper, the metal copper and copper sulfate, which was in blue in color. So the characteristic, the physical and chemical characteristic of the element and the compound are so different than each other. Another example of that is sodium chloride. Usually, now definitely there is easier way to make sodium chloride. This is, we call it the hard way of doing sodium chloride, which is the table salt that we eat. It's by the reaction of the sodium that we talked that it reacts violently with water, plus Cl2 gas, which is poisonous. When they react with each other, they form the NaCl solid, which we can eat. And this just explains the fact, the properties of the elements. This was very reactive with water. This is poison. We end up with something that we can eat. So the chemical and physical properties of the elements and the compound are different from each other, totally different from each other. Now, the formula. Usually whenever we're talking about chemicals, we're going to represent it as formulas. The formula, usually it's going to be, let's say we have atom A and atom B. It's always going to be AB or A2B or A3, B2, whatever it is, but it will never be a fraction. You will never see a fraction in a molecular formula. You would see it in empirical formula, that we're going to talk about by Wednesday, but you never see a half or a quarter or something in a molecular formula of a compound. It's always it is kind of an integer, okay? In there. And that brings us to what are the bonds. So the bonds between the two bonding that we're going to talk about in this course is ionic bonding and covalent bond. So in an ionic bonding, I have, let's say, A and X. Okay, I have A plus X minus. Where A, so the main idea in here is that one of those lost an electron, totally lost an electron. The other one gained an electron. It can be 2 electrons, 3 electrons, 4 electrons, it depends what we have. But ionic bonding is all about losing and gaining. So A lost an electron, it's A plus, X gained an electron, it's X minus, and the only interaction between them is electrostatic forces. Ionic bonding usually takes place between group 1A, 2A from one side, and the metals of group 3A with not within each other, not 1A with 2A, it's 1A with 6A, 7A, the non-metals of those, and 5A, the non-metals of those groups. Okay? So this is where ionic bonding takes place. And we're going to talk in details why is that the case and everything. But this is kind of the general idea. Now, covalent bonding. Ionic bonding is losing or gaining. Covalent bonding is sharing. So the electron, for example, if I have fluorine, F2, neither one of the fluorine lost an electron. They put the two electrons in between them and they share it. Now it could be an equal share or non-equal share, and that's gonna cause polarity, which we're gonna talk about later on during the chapter. So the covalent bond is sharing electrons. So none of those atoms lost or gained electrons. They just put the electrons in share between each other, sharing. Now, covalent bonding usually takes place between 4A, 5A, 6A, 7A, in between each other. Like something from 4A with 6A, 7A with 7A, which is a fluorine, this is 7A, 7A, or 6A, 7A, some of the 6A with the 7A, together they form these covalent bonds. And definitely we're going to talk more in details how that happens and why. So this is the two kinds of bonding that we're going to talk about, the ionic and covalent bonding. Now let's start with the ionic compounds and talk a little bit more about them. So in ionic compounds we have ions. They are formed from ions. The ion that elements will gain electron and possess a negative charge to be like a noble gas, and these are called anions. So A will gain one electron and it will be A minus. And we call this A minus the atom when it have a charge, a minus charge, anion. I'm gonna stop in here and comment on one thing. This happens every semester. For a long time, every semester, that whenever students see A minus, because it's a human mind to think that minus is lost, they think that A lost an electron. It's not the case. Here it is A minus, that means A gained an electron. It has one more electron than when it is neutral. Look at this, A plus 1 electron, it is A minus. Remember when we talked about the atom having equal number of pluses and minus, neutrons equal to number of protons equal to the number of electrons in a neutral atom? Now you added one more electron to that atom, and this is why it has the minus charge. So whenever you see A minus, any atom minus, that means that atom gained one electron. Okay, and it is called an anion. Now, elements lose one electron to have to be an X plus, and they are called cation. And the plus doesn't mean that it gained an electron. That means now it has one proton in excess because it lost one electron. Okay? So those are the definition of cation and anion. Anion is an atom that gained one electron. It could be 1 or 2 or 3 electrons. It's not exactly 1 electron, but it gained electrons. And the cation is the atom that lost either 1, 2, 3, 4 electrons, and it is called cation. And as you see here, I said they lose or gain electron to look like a noble gas. And I'm going to comment on this in a minute. What does that mean, that they want to look like a noble gas? Now here is kind of a joke, a chemistry joke, that just to always keep a track that something that lost an electron, it is positive. That's the joke. You can read it. It's there. So since it lost an electron, it's positive all the time. Okay? Now, let's predict. Let's say you have this periodic table. You can, from the periodic table, predict the charge, whether it is whether it is a plus charge or negative charge. The second thing, whether it's gonna be like an A plus or an A2 plus. So all group 1A, they're gonna lose one electron. They tend to lose one electron. This is why all of them, they have X plus as a cation. Why they do that? If they lose one electron, they're gonna look more like electronically, and we're gonna talk about electronic configuration and how to write that in chapter 6. When they lose one electron, they will have exactly the electronic structure as the noble gas. And the noble gas are the happiest out there. And every elements want to be like 8A, like the noble gases. Why? The noble gases are so satisfied, they don't want to do any reaction. This is anything in this periodic table, whether it's sharing or losing or gaining, it's doing that to look electronically in the electronic structure as the noble gas. Group 2A, except the beryllium in there, all of them, so not the beryllium, but that includes everything there, they all lose 2 electrons. Why do they lose 2 electrons? Because if they lost 2 electrons, 1, 2, they would look like the noble gas. Okay? Now, from 3A, aluminum is the one that we can predict. Definitely, this is metalloid, so it's not gonna do ionic bonding. But this, since it is a metal, it's gonna do ionic bonding, and its charge is 3 plus. Okay, because if it lost the 3 electrons, it's gonna look like a noble gas. Now, as we go to 5A, those are gonna gain electrons. Okay, so this part of the periodic table, they're gonna lose electrons, so they are cations. And this part, they're gonna gain electrons and they're gonna be anions. And this is only, they will be anions if they are in a compound with something from 1A, 2A, and 3A. Nitrogen can do both covalent and ionic bond. It depends with which it is in a compound. Is it with one of the 1A, 2A, 3A, or 5A, 6A together? Okay? But when they do 5A, 6A, and 7A, the non-metals, not the metalloids, not the metals, the non-metals of those, when they form ionic bond with group 1A, 2A, and 3A, they're gonna have a 3 minus, and I think everybody predicts why is that the case, because 5 plus 3 is gonna be, they're gonna look electronically like the noble gases. The same for 6A, the non-metals of 6A, if they gain 6 plus 2, if they're gonna gain 2 electrons, they're gonna be 8A, they're gonna look electronically like the noble gases. The same for the halogens. I'm gonna comment on this hydrogen in here in a minute, but let's first talk about the other halogens. The other halogens, as you can see, they all have 1 minus as a charge. And this is because if they gain 1 electron, because a minus means gain, if they gain 1 electron, they will look like a noble gas. Okay? So we can predict all these cations and anions charge just by looking into the periodic table. Okay? Now, for transition metals, it's much harder to predict the charge for one good reason, because they can be in more than one cationic form. And all the time they are in the cationic form. You would never, for example, see chromium 2 minus. That's wrong. You would never see, for example, nickel minus 1. That's never going to happen. They're going to be always cation. They're going to always lose electrons. For example, chromium, it has 2 forms or 2 forms of cations. Chromium 2 plus 3 plus, Fe, Fe2 plus, Fe3 plus. So it is hard to predict. Cobalt 2 plus, cobalt 3 plus. it's only Ag, which is the silver, always exists as Ag plus, not Ag2 plus or 3 plus. This is the only one that we can predict. As you can see, the others also have more than one. Now we're going to learn how we can figure out how much is the charge if we're given a name or something. We're going to talk about this in a minute. Okay? So, as a conclusion, metals of 1A, 2A, 3A will lose electrons forming cations. The non-metals, which are from group 5A, 6A, 7A, they're going to gain electron to forming anions. Usually, the charge is predicted that we always going to be, they're going to look like how much they need to look like a noble gas. So, here is kind of the summary of what I said, but in wording, and we call those monatomic cations because they are just one, they aren't polyatomic. We're going to see the polyatomic in minutes. Group 1A, 2A, and only aluminum from 3A, they form the cations. Example of that, 1A lithium loses 1 electron. Group 2A, they're going to lose 2 electrons to look like a noble gas. The same for 3A, only aluminum from 3A is going to lose 3 electrons to look like a noble gas. Okay? Now, transition metal, as I just said, it is hard to predict their charges. Those are the most common that you're going to see in this course. Iron 2 plus and iron 3 plus, so it can either lose 2 electrons or 3 electrons. Chromium 2 plus or chromium 3 plus. Ag, silver is the only cation form is Ag plus. Copper, it can exist as copper 1 plus or copper 2 plus. So it's hard to predict for transition metals. Now, the only polyatomic, there is a lot out there, but the only one that you're going to see in this course, just because this course is not an extensive one, the only polyatomic cations, and I mean by polyatomic that it is consisted of more than one atom, is the ammonium cation, and this is the ammonium cation. Guys, I think at Friday we handed in this weight sheet for you, and it's going to be useful in a minute, so if you can take it out, make it ready. Okay, so this is the two kinds of cations, polyatomic, or it's not really necessary to know this classification, but now how we name cations? If I have a cation, like sodium plus, how can I name it? It's exactly, you use exactly its name followed by the word cation. Calcium. It's calcium cation. Aluminum cation. And as you can see, those 3 examples that I'm giving in here are from the main group. That means from group 1A, 2A, 3A. Now, when it comes to the transition metals, for all of these, it's clear. When I say sodium cation, it's definitely going to come to your mind, oh, sodium is group 1A, so its charge going to be 1 plus. Calcium is group 2A. As a cation, it's going to be 2 plus because it belongs to group 2A. Aluminum, when I say aluminum cation, it's directly going to come to your mind that it is 3 plus as a charge. But when we talk about transition metals, like cobalt cation, when I say cobalt cation, how are you going to know which one I'm talking about? And this is where the nomenclature comes into place. When we're naming transition cations, transition metal cations, we're going to write in between 2 parentheses the charge in Roman. In Roman number. Okay? And this is the case all the time. This is how we understand each other, which cobalt I'm talking about, which chromium I'm talking about. So whenever you're naming the transition metals cations, you're going to represent between 2 parentheses the charge. Okay, and it must be in Roman. It couldn't be, for example, here, right 2. That's going to be considered wrong. Okay? So here is how to name both chromium 2 plus and chromium 3 plus, and we followed that with cation. Okay? Now let's see how we're gonna name the anions. We already talked about this, which how much is the charge. Now, the charge of the anions, usually the charge of the anions, not the anion, equal the group number minus 8. What does that mean? For example, if it is a group 7, 7 minus 8, the charge gonna be minus 1. So all of group 7A gonna be minus 1. Okay, for the same reason that if they gained 1 electron, they're gonna look like a group 8 electronically in electronic configuration like a group 8. Now, the way that this is an example of all group 7A having a minus, a 1 charge minus. Now, how are we going to name those? We learned how to name the cations, how to name the anions. So, to name the anion, you take the name of the, for example, let's say F minus. How are you going to name this? You get this, the name of the atom is fluorine, so you're going to cross the "ene" and put fluoride. For example, N3 minus, nitrogen, you're going to cross it, and nitride. And there isn't a rule that it must be the last 3 letters. There isn't a clear rule where exactly you cross and put the ID, but usually, mainly it's the first syllabus of the, you keep the first syllabus and then cross the other and put ID. Sulfate, 2 minus is going to be sulfide. Oxygen is going to be oxide. Okay, this is how we name anions. Okay, so we learned how we name cations, which is the name of the atom as it is, followed by the word cation. If it is group 1A, 2A, 3A. If they are transition metals, we must put between 2 parentheses the charge in Roman numbers. If we're naming the anions, we take it and cross part of the word and put ID, fluoride, nitride, sulfide, oxide. Now, we're doing all of this to know how to name an ionic compound, right? And this is what we're gonna do now. Sorry. Before we go any further, there is, in addition to those anions, there is what we call oxoanions, and those are the anions which have any element from the periodic table, and in addition to it, oxygen. And those are the polyatomic anions. Now, those, they don't have a specific way to name them. They are out there. You need to know the names, and this is where the handout comes helpful, because I already kind of summarized most of the oxoanions or polyatomic anions. I put the names in there, and there is kind of here a table. Fill that table because it's a good practice for you. I'm gonna post the answer key for this maybe next week, sometime next week. So this, as time goes on, you need to know those. By the time we have exam, you need to know all of these. Now I'm just gonna give you some kind of clues.
Yeah.
And my apologies. So I'm gonna just give you some clues out there. For example, NO3 minus, it's called nitrite ion. NO2 minus, this is nitrate, and this is nitrite. So usually whenever we have, for example, both of them, they have nitrogen. One has one more oxygen than the other. When it has more oxygen, we usually use the 8. When it is less, we use the I. Definitely there are exceptions out there, but this is kind of the case. PO4 3 minus is called the phosphate ion. You need it just to learn it. There is no good way. Sorry. For example, this is called the hydrogen phosphate ion. OH minus, it's called hydroxide ion. Sulfate, again back to the 8, and sulfide ion. Cn minus, known as cyanide ion. And you need to know those. Now, how are we gonna name? Do we need one more minute? Okay. we learned how to name the polycations, the polyanions, the cations, the anions. Now how to name the ionic compound. So, for example, let's say you have the formula this, CaF2, and I asked you what is the name of that. What you're gonna do is you're gonna name the cation and the anion, and that's how we name ionic compound. For example, this is calcium fluoride, because this is fluorine, and I'm gonna cross the 3 letters there and put IDE because this is how I name the anion. Usually, always, ionic compounds, cations, is written as a as a formula, cation, and then followed by anion. In case you don't know, I'm assuming you know, but in case. Okay? So, we're gonna do some practice on this. What's going on? Okay. For example, MgOH2. So, first of all, you know that this is magnesium. And you go back to the table or to the slides where I give you the OH, it's hydroxide, so it's magnesium hydroxide. Okay? This is how we name that. Okay? Now, how to get to this molecular formula? Let's say I asked you, I'm going to insert in here, let's say I said barium chloride. And I asked you, I gave you, this is barium chloride, and I asked you to write the formula of barium chloride. How are you going to handle it? So, our first step is say, okay, barium. Barium is Ba. It is in group 2A. That means it's going to lose 2 electrons to look like a noble gas. Chloride. Chloride is group 7A. Chloride should have a -1 because if it gained 1 electron, it's going to look like a noble gas. Then I say, oh, I have barium 2 plus and Cl minus, 1 Cl minus, but that's not balanced because I have 2 plus charge and here I have -1 charge. So I need 2 chlorines, 2 chloride ion to kind of balance that 2 plus. And this is why we look after figuring out the charge, we look, is that balanced? No. If it is 1 plus 1 minus 1, that is, the formula gonna be barium chloride. But if it is 2 plus minus 1, it isn't balanced. So what you do is take that number in here, this is here, and that's gonna be your ionic formula. Barium chloride 2. Okay? And this is what you need to do for every time I give you a name and you need to translate it into a formula or a formula into a name. Okay? So these are the steps that you definitely now I'm doing the steps in a very slow way. In real life you're gonna go way faster than this, but just I'm kind of showing you the basis. And after that, in your mind you're gonna do all of this in kind of 30 seconds. Okay? So this is the formula of barium chloride. Here is the detailed one. So step 1, figure out barium is group 2A, it have a 2 plus, chloride group 7A, Cl minus. Then you look whether the charge is balanced or not. So if you have 2 plus, you must have 2 minus out there. And then this is how you figure out the ionic formula. Okay, that's a shortcut. Now, lithium phosphate. Try to write down lithium phosphate. Definitely you need the handout to know what is the phosphate. Till now you don't know what is the phosphate. So, lithium. Look, where is the lithium? Lithium is group 1A. So it's going to have 1 plus because it's going to lose 1 electron to look like a noble gas. Then phosphate, PO4, 3 minus. Then you're gonna look, okay, we have 3 minus 1 plus. So I need 3 lithiums to kind of balance this charge, or in an easier way, you can take this 3 here and this 1 into here, and you end up with lithium 3 phosphate. Usually we don't put brackets on around the polyanion unless we have 3 or 4 or 5. We have an index for the. But if it is 1, we just keep it without any brackets. Now let's go to number 2 in there. Iron 3 perchlorate. So first iron 3. So because it's a transition metal, they put between 2 parentheses the charge, because I wouldn't be able to figure out the charge by myself. So it is Fe3 plus perchlorate. You look to the, definitely by time you know that. This is the perchlorate. Then again, you need to balance the charge because it's not balanced. So you need 3 more chlorates to balance that. So it's going to be FeClO4, and I need to put the brackets in there, and 3. The more you practice, the better you get in this. Now, it's the other way down. I have the formula, I need to write the name. Okay? So what I'm going to do first, the name of this is aluminum. And this is phosphate, so it is aluminum phosphate. And since it isn't a transition metal, I don't need to put the number between 2 parentheses, the charge. This is aluminum chlorate. And as you can see, I don't mention anything about 3, about 1, that I have 1 aluminum. Why? Because the name by itself, if I'm writing the formula, is going to help me. The ionic formula is going to help me to balance it. The last one, what about you try the last one? Write the name for the last one. Okay, so it is Fe. If I search where is Fe, Fe is a transition metal. That means I definitely have to write in the name the charge between 2 parentheses. So Fe is iron. And how I'm going to figure out the charge? What is the charge there? 3, very good. The charge is 3 there, and I knew that from this number in here, because I know that the permanganate, that MnO4 have 1 minus. So definitely, since I have 3 of them there, that means that must be 3 plus. So iron 3 permanganate. Yeah. So get the idea? Now let's do an eye clicker. I'm going to stop it at 1 minute. This is the time in here. So I have 67% for C, and 20 for A, 12 for B, and 2% for D. So C is the right answer. So I have cobalt. It's clear that it is 2 plus. Carbonate is CrO2 minus. The 2 plus is balanced by a 2 minus. So I don't need to do anything. It's a balance. It's cobalt, carbonate. Okay? Let's do one more. A, B, C, D. Okay. Again, 1 minute. Okay. I'm going to stop it at 120. So okay. Okay, I have 86% for B. B is the right answer. Sulfate, aluminum, and I have oxide. So aluminum belongs to group 3A, so it must be 3 plus. Oxygen belongs to 6A. If it gained 2 electrons, it would look like a noble gas. Now I see that they aren't balanced. The plus and minus are not balanced. So it's going to be Al2O. Okay? Okay. Now one more. But this time the question is different. What are the ions of which Na carbonate, sodium carbonate is formed? So I'm asking, what are the ions from which sodium carbonate is formed? I'm going to stop it at 120. Yes, you need to know all of these for any test. It wouldn't be given to you in a test or any exam, all the 5. Okay, let's see what did we do. I have 86% for D, and D is the right answer. So this is a very important question, not because I'm going to ask about, usually I ask about it in exams, but it is important for later on in chapter 4. So this sodium carbonate is made of sodium plus and carbonate 2 minus. No, it's not made of carbon 2 minus or 2 minus, that's wrong. It's only made of sodium and carbonates. In other words, if I take the sodium carbonate and I put it in water, what I'm gonna get is sodium plus and carbonate. It happens that when we go to chapter 4 each semester, I find some students that they think that when they put this in water, it's gonna go to sodium, carbon, and oxygen. No, that's not the case. That's not gonna happen. What's gonna happen is when you put the stuff in water, ionic compounds in water, if they are soluble, they're gonna go to their ions, not to their atoms, not to the atoms, to the ions. So definitely all the others are wrong, and they aren't the case. You have to keep that in mind. This is applicable for any compound we talked about today, ionic compound that we talked about today. Whenever you put it in water, it goes back to its ion that from which we started to name it or to put to the formula together. Molecular compounds. Okay. Okay. So I'm gonna get started with this on Wednesday just because it needs more than 10 minutes to finish data. So I'll see you Wednesday.